Welcome back to ECE 320A. We do have an exam a week from today, and in anticipation of that, and also the fact that we have our 5th homework assignment due on Tuesday, I'm holding special office hours Tuesday morning from 9 to 11, if that would be of help to you. So your homework is due on Tuesday, and that's essentially inverse Laplace transforms. I'm not sure when we can have a review session. My schedule is fairly full, and so we'll vote on that at some point during the class period when you're all asleep. We'll wake you up with a vote. I don't know how many of you voted on Tuesday, but I'll give you a chance to vote on Thursday. How's that? There was a primary, I think, on Tuesday. And again, the exam number 2, which will be topically covering material since exam 1. So there will be some end of chapter 11 material, which is the power, the 3-phase power stuff, and then we'll do the chapter 12 material up through inverse Laplace transforming. Today what I want to talk about is case number 2 for inverse Laplace transforming, which means repeated roots, and how you find residues or how you find those partial fraction expansion coefficients. You can do it many different ways, and this allows us the opportunity to discuss that when we get into repeated roots. If you have simple roots, case number 1, which we talked about last time, that's about the most direct way to find those residues. But there are many ways of finding those partial fraction expansion coefficients, and we'll talk about 4 of those, hopefully, dealing with case number 2, which you do have to find a different way to determine one of those or several of those coefficients if you have repeated roots. The first one we will talk about is a convenient value of S. So hopefully you're aware of convenience stores. Well, now we're going to create a convenient way of finding one of those coefficients by selecting a convenient value for S. And by convenient, essentially what that means is whatever makes your computation easier for you. But you also have to make sure that it doesn't cause you problems in the computation. Then the second one that we will talk about, and these will become more clear when we get into those, is looking at a limiting expression. After we multiply both sides by S, let S go to infinity. That will allow things to be identified that hopefully we can then isolate the unknown coefficient from that information. You can also find these partial fraction expansion coefficients, all of them, by using the third technique, which is a common denominator technique, and we'll illustrate that. And if you have a calculator that does matrix inverse, you could then just brute force the procedure and end up with these coefficients. And finally, the one that's discussed more in the textbook is the derivative approach to finding or isolating these coefficients that are associated with repeated roots. Let's repeat or return to where we were last time with case number 2. I think we had just started that. Case 2 is concerned with, again, inverse Laplace transforming. And we had looked at a particular transfer function, f of s, which we said, okay, let's let the root p sub 1 be repeated, and let's say that it's repeated twice. If you were sketching poles in the complex S-plane, you would have 2 x's right on top of each other. Typically, I draw those a little staggered from each other just to emphasize that there are 2 poles there, but they are physically right on top of each other. If we had two poles at the origin, I might show two x's next to each other, but the intent is that they're right on top of each other and they're at a particular location. In this case, you have two poles at a value of s such that that denominator vanishes, or when s is equal to minus p sub 1. The other third term, which appears on the screen when I'm doing this in the office, but when I come into a different projection system, the resolution is not quite as nice. But now we have a sub 3 over s plus p sub 3. As we, I think, talked about last time, we can identify a sub 3 using the case 1 approach, and we can also identify a sub 1 or evaluate for a sub 1 using the same kind of technique. And the case 1 approach is you multiply both sides through by the factor in the denominator, or the expression in the denominator, and then evaluate both sides at the value of s where that expression would vanish or disappear. And that's what I've done here for this particular example. In a sub 3, for a sub 3, we can find that using case 1. I think we talked about that last time. Again, multiplying by that factor, s plus p sub 3, which originally was underneath a sub 3, and then evaluating that result, and that result means that you're going to cancel that factor in the denominator of your original expression, which leaves you then with the numerator polynomial divided by everything in the denominator except the factor that you're trying to find or identify its residue for, and you evaluate that expression. Everywhere you see an s, you replace that s with a minus p sub 3. That will give you the a sub 3 coefficient. And if if p sub 3 was complex, you could expect a sub 3 to be a complex number. But if p sub 3 is complex, what do you know should be the case in a given transform? There should be a conjugate pair, and the reason you have conjugate pairs is because we're assuming we have real coefficients in our polynomials. If you have real coefficients in your polynomials, if you have one complex pole, you're going to have a conjugate associated with that complex pole. And if you find one of those, you simply have to conjugate that residue to find the complementing residue for the conjugate pole pair. Case 1 well, here, let me expand this. That's the problem with doing this before class. The case 1 formula works for the coefficient associated with the highest power of the root. And in this particular example, that was the a sub 1 coefficient. We multiply both sides through by the s plus p1, in this case squared. We just had two poles at the same location. And for the structure that I had assumed in this example, that's the numerator divided by what's left over in the denominator when you cancel everything out that you've just multiplied through by. And that just leaves us the one factor, s plus p sub 3, in the denominator. You now evaluate that at s equal minus p sub 1. Questions on finding or using case 1? That's how you will work the majority of your problems, is using that particular case. Now, to find a sub 2, if you remember what a sub 2 was, a sub 2 is associated with that repeated pole, except it's now not the highest power of that pole. So a sub 2 is problematic because if we multiply through by s plus p1, we can't let s equal to minus p1 because then both sides would be going to infinity, and infinity equals infinity, but we can't evaluate a sub 2 from that information. We need to do something else in order to solve for this coefficient a sub 2. And I'm going to just state that there are many ways of finding that coefficient a sub 2. And at this point, we can assume that we've already found a1 and a3 using what we've just done, the previous case 1 applied to a1 and a sub 3. If we are at that location, let's now look at an example where this is now the case for repeated roots. And in particular, let me just say that f of s is now this 2s plus 1 over s plus 1 squared s plus 2. And as a review, what's the partial fraction expansion look like for this particular transform? That's one of the pieces. How many pieces do you expect to have? 3, because your denominator polynomial is third order. You're expecting 3 pieces. In the convention that we've established, what's the next factor or expression look like? We just keep decreasing the power of that repeated pole factor until we get down to the power of that factor being equal to 1. And so we've gone far enough with that repeated pole at this point. And then we end up with something like that. Now, if you're out of time on an exam and you're asked to find f of t, you could very quickly write down the f of t, and I might just ask you, what's the structure of f of t, little f of t? I might give you a capital F of s and say, what's the structure of little f of t? And what I'm looking for is that for you to then recognize that f of t, you know pretty much what there is to know about that except for the coefficients associated with those terms in the time domain expression. If you now inverse Laplace transform the a3 term, what do you see? What's a3 going to be scaled by? A decaying exponential, and you know exactly the decay rate on that exponential. It's minus 2. The only interesting thing is when we have these repeated roots. In this case, we will have a1 t e to the minus t, where this 1 is right there. It's not explicitly shown, and the fact that we have this 2 is what's giving us this t. And if you go to the cube, then you're going to have 1/2 t squared e to the minus t, for example. There becomes some more coefficients in there other than just the t squared, etc. There's a scaling factor, and we may talk about that in an example later. The next piece that you could then immediately write down is simply a sub 2. That's in the case 1 form. And finally, the a sub 3 term. And this is then Now, if somebody gave you that expression, you know what these terms look like, I assume, in terms of structure. These are the decaying exponential. What's that first term look like? T e to the minus t. What's t do as a function of time? It just goes up. But what's e to the minus t do? That goes down. Which one is more dominating for high values of t? T or e to the minus t? E to the minus t. So you're going to get a bump and then a decay from that first term or expression. And when would you expect this f of t to essentially be gone? If you were watching it on a screen, when would you say, okay, it's over? Would it be a long time? Would you have to sit down and put your feet up and watch it? Or would it be pretty quick? And what's governing that decay, or that length of time that f of t is effectively non-zero? Whoops, that's not a question mark. I want to be practically speaking. I'm not questioning that. So in a practical sense, if you have a large number of terms that all are decaying exponentials, what do you start doing when you say, well, when is this going to be gone? So now in 220, did you talk about time constants? And what determines or what governs a time constant? If you had I'm sort of going aside. This is, oh well. So let's say that we have e to the minus alpha t. And somebody says, oh, now I'm really going. But see, there's all sorts of fun things. You could just talk forever with a napkin and a marker on these topics. In the complex S-plane, where would this appear, or where would you associate that expression as a pole? That's associated with a pole. And where would you find that pole in the complex S-plane? On the imaginary axis, on the positive real axis, on the negative real axis? If you took this if you Laplace transformed that, what do you see? Now do you know where the pole is? It's where that factor vanishes. Now you're looking at the value of s that causes that denominator to vanish, and now we can go to the circus because we know exactly where that pole is. Yes? So now we know where that rubber sheet is sticking up. And that's going to be sticking up at this distance minus alpha. Now, that's not the time constant, so I'm really jumping around. How do you determine the time constant? Well, it's the time value, so it's the value of t when that exponent equals 1. So you're looking at e to the minus, and you want that whole expression to be 1. And what value of time t causes that to happen? So if you say my exponent is equal to alpha t, and you want to know what's the time constant, you're saying, oh, I want alpha tau to equal 1. Or tau, that's your time constant. Tau in seconds, 1 over alpha. If we go back to our earlier example where we had, let me just take, well, these are maybe, we had those two exponential decays in our expression. And now do you see physically where the poles of those would be in the complex S-plane? Do you now physically kind of see where the poles are just by seeing that time domain expression? One pole is at -1, the other one's at -2. And which one of those poles has a faster decay rate? This one's going to decay faster, isn't it? So if somebody says which of these poles dominates, it's going to be the slow one. This is the one that's going to dominate your time response. And where is that pole relative to the origin? It's closer to the origin than the one at -2. Meaning the further you get away from the imaginary axis, the further you move into the left half plane, the faster those roots are decaying. That making sense? If somebody now said, okay, how fast or how long are you going to see that f of t? What's typically given? This, okay, so now this time constant, let's say this is tau 1, is equal to, that's 1. What's this guy's time constant? So now we have a time constant of 1 second and a time constant of 1/2 second. So that pole at -2 is twice as fast as the pole at -1. And how many time constants do we need to wait before we sort of say practically that's gone? 5. Is that what you learned in 220? So if you wait for 5 time constants, that's like saying you're at e to the -5. Because you now have, if you viewed this, you would have e to the minus t over tau as an expression, and you now wait for t to be 5 tau. You now have an e to the -5. And what's that numerically? What's the numerical value for e to the -5? You should have this memorized. So now pull out your calculators and tell me what that is. I don't have it memorized. But what do you think it should be? It better be small if we're saying it's practically nothing. And what is it? So typically they say that's like 1%. So you're less than 1% of where you started. Did you guys get that? 0.0068 for e to the -5. Sometimes people may use 4 time constants, and that's roughly 2%. So if you started at 1, you would be at 2% of that in 4 time constants. In 5 time constants, you're at 1% of where you started. In this case, how many seconds do you need to wait before this f of t is practically gone? 5 seconds. So you're not going to sit down and get too comfortable before this f of t is gone. Just 5 seconds. And if you had a sinusoidal source that you applied to this, and you had poles with time constants of e to the -1, you're going to reach steady state in 5 seconds. Meaning, here's a circuit, and now I start shaking it, and that was supposed to be periodic, if you could tell. That was a sine wave, and it was repeating consistently at a certain period. It gets into sinusoidal steady state after the transients have gone. In 5 seconds, you're at sinusoidal steady state. That's why you spend so much time worrying about sinusoidal steady state analysis, because you don't have to wait too long before you're there. Is that making sense? But now you're learning what happens in between the application of the signal or the input and the sinusoidal steady state. That's what this course is trying to talk about. What's happening in that transient interval. But now you know it's 5 tau long, and in this example with poles at -1, so you look at the dominating pole, and in crude terms you sort of discount all the others. You look at the pole closest to the origin and say this one's dominating, and say, okay, let's assume what our time duration is based on that pole. Now, that was not where I was wanting to go, but did that help? Now you know a little bit more about these time constants and why maybe it was -5, or why you had to wait 5 time constants for your system to be in a sinusoidal steady state condition. If we now evaluated, let's go back to what we had. We had f of s was equal to 2s plus 1 over s plus 1 squared s plus 2. I think that's what we had to begin with. And we said we had an a1 s plus 1 squared and an a2 s plus 1, and then we had an a sub 3 s plus 2. What's a3? We can get it fairly quickly. We just multiply both sides through by s plus 2 and set s equal to and in this case, we don't even need a Ti-89 titanium, do we? For that, we can probably compute that number. We have -3 over 1. And what about A1? We can get that exactly the same, or similarly. Now we multiply both sides by s plus 1 squared to get rid of that piece. And we have 2s plus 1 over s plus 2. We evaluate at -1. Now we have 1 downstairs and -2 plus 1 upstairs, or -1. And we found quite a bit. We found 2/3 of our answer, right? Now we have to do the hard part. The next part, well, it's not that hard, but now is what I want to cover, all the different ways that we could find a sub 2. We can't apply that same approach. Case 1 doesn't hold. So now you can pick any value for s and plug it into both sides and then solve for your only unknown, which is a sub 2. And that's that convenient value of s. So that's technique number 1. Let's just do that. So now this first technique is and here we are going to select and I'm calling this the convenient value approach for finding a sub 2. If we go back to our example, since I do not have a pole at the origin, my denominator is going to be well behaved if I selected s equals 0. And if I put s equals 0, a lot of things are going to fall apart, but nothing's going to blow up. If I had a pole at the origin, if my denominator had an s sticking out there by itself, or an s squared, I couldn't use 0 as a convenient value. Does everybody see that? I might be able to use 1. I can't use -1, can I? I can't use -2. But you could even use -1/2 if you wanted to, and that would get rid of that left-hand side. s equal minus 1/2, then my left side is all 0. Does everybody see that? There are many different convenient values. It's just whichever one you see and you think you want to work with. Let's let, in this case, s equal 0. Now I plug s equal to 0 everywhere. In the left-hand side, I had 2s plus 1 upstairs. I had s plus 1 squared and s plus 2. And I've assumed that I've already found my a1 and my a3. So I'm going to plug in the a1, which was minus 1. I don't know a sub 2, but that was over 0 plus 1, or s plus 1. So a sub 2 is just over 1. And I had an a sub 3 of minus 3 over 0 plus 2. Maybe I should have put this like that so that you see the strategy that I'm applying. Is that clear? And now what do I have? Well, over on the left, I have 1/2. I have minus 1 plus a sub 2, and I have minus 3/2. Oh, that 3/2, when I move it over with the 1/2, I get 2, and then I add in another 1. So a sub 2, I hope, if I'm processing properly, that should be 3. Is everybody okay with that? And now we're done, really, with f of t. We now know that f of t is a1 was minus 1, a sub 2 was 3, and a sub 3 was minus 3. And that's now, we could be done. Question? Okay, the question was, I thought that the instructor said we couldn't use 0. I said you can't use 0 in certain cases, and you can't use 0 when, do you remember? The rest of you remember when you can't use 0 in this approach? When you had s by itself on the bottom, when you had a pole at the origin. And in this example, we didn't have a pole at the origin, so s equals 0 was fine. And that's probably a good convenient value to use unless you have poles at the origin. Yes, you can't use it, s equals 0, if you have a pole at the origin. Pardon? You can't use the roots of your denominator, because then you're going to get infinity equals infinity, which is true, but it doesn't help you. Okay? So you can't use the values of s that cause your denominator to vanish, or what we call the poles of our transform. Let's now look at another case. Now that we know the answer, now it's fun to just kind of explore. So let's, well, to each his own, I'm sure you're thinking now. Oh, brother, he thinks this is fun. So, 2, another approach. This is going to be what I'm calling the limiting expression approach. And here's the technique. First, or A, we are going to multiply both sides of this partial fraction expansion by the complex variable s. That's going to be in all the numerators now. So I multiply both sides by s. And that is what? That's a 0. That would be a 0 at the origin, which is just the opposite of a pole at the origin. But now we would have a circle or a thumbtack at the origin, is if we needed to do it. But here we're just looking at it, and then we're going to let limits happen. The next thing we do is on both sides of the equation, we take the limit as s goes to infinity. because the partial fraction expansion is valid for all s, let's just let s go to infinity. Okay? Once we have that, hopefully things will start to go away. Certain things, certain terms will vanish, and maybe we'll have an easier task of solving for this unknown a sub 2. Now, if those steps, A, B, and C, are not very clear, let's apply those to our expression. We had 2s plus 1 over s plus 1 squared s plus 2 equaling a1 over s plus 1 squared plus a sub 2 over s plus 1 plus a sub 3 over s plus 2. That was our partial fraction expansion formula. But we've already determined what this is. This was minus 1, and this was minus 3. And we can plug those in. What we don't know is a sub 2. And we've already found the convenient value to solve, but this is a different technique. This approach says, oh, multiply all terms by s. So let me put an s there, let me put an s here, an s there, and an s there. Now, here's the fun part. What happens when you let s march off to infinity? Let's just look at an easy term to begin with. Let's look at the first term to the right of the equality sign, and let's let s go to infinity. What's happening there? We have a minus s upstairs, and we have, what term is going to dominate? The s squared term. We have an s squared plus 2s plus 1 down in the basement. But s squared, as s goes to infinity, s squared is going to dominate the s term and the constant term. So effectively, we have s over s squared, or we have 1 over s. And we're letting s go to infinity. That's going to vanish, isn't it, that first term? Does everybody see that? Let's now move back onto the left-hand side of the equality sign and say, okay, what happens as s goes to infinity here? And I'm going to be sort of loose with this, but I'm going to say now I'm limiting, or I'm looking at the limit as s goes off to infinity, and I'm going to apply it to all of these terms. What are you concentrating on that left piece? You're looking at the highest power of s, aren't you, in the numerator and the denominator. In the numerator, what's your highest power of s? You have s times 2s, so you're going to have an s squared term upstairs. What do you have downstairs? S cubed. So now you have s squared over s cubed. That looks like 1 over s. What's that going to do as s goes to infinity? So now you just look at those values of s, and if the bottom's bigger in numerical value, you know it's going to go to 0. Now, we already said the first term was going to go to 0. What about the second term? It's going to go a2s over s. And s is going off to infinity at the same rate, so those two s's cancel, and we're left with a sub 2. Everybody see that? What about the next term? Now we let s march off to infinity, and the numerator and denominator are the same order. Those are going to move at the same rate, and they are scaled by this minus 3. So 0 is equal to a2 minus 3, or a2 is equal to 3. Isn't that what we got before? And that one's not too hard either to use. Multiply everything by s and let s go to infinity, and a lot of times things start falling out. Now, if I had that before, did everybody see what I just inserted? If I had a 2s squared plus 1 to begin with, what would my left-hand side have been equal to? Does everybody see that it would have been 2? That was maybe a poor choice, well, of coefficient, but I'm not going to leave it there so that you don't get confused. All right. Uh-oh, somebody fell asleep. Which means that we need to take a vote. All right. So now we're going to vote on, so this is your in-class participation. I want you to vote, well, I don't know if any of these make sense, but either say Monday, which is the 5th. Can anybody come before 4, or I'm sorry, before 5? Does that make sense, before 5 on a Monday? For some of you? Okay, so let's say 4 to 5, 5 to 6, 6 to 7, or 7 to 8. Or do you want to go later than 8? All right, so those are your options on Monday. Tuesday, there's already things going on Tuesday, and so that's why maybe you remember the engineering open house in 102. That's happening. So you're only allowed 7 to 8. Oh, and these are PMs. Well, I mean, I could be here at 4 a.m., but I don't know if you guys would. And the janitors might get upset when we start all in mass going upstairs. I don't know if the elevators are open quite that early. So I'm assuming these are PM time slots. Tuesday, that's really the only one we have. And hopefully I'll still have a voice. And then Wednesday is 6 to 7. Well, there's an IEEE meeting, and I'm assuming it might end by 6. It may not. Or 7 to 8. Or would you just prefer that I sit in a room and record a lecture and make that available? So the other option is... What? Oh, I'm a lonely guy. So is it not working? So maybe that might not be a good option. So you have however many slots I've identified. You have 4 on Monday, 1 on Tuesday, 2 on Wednesday, and you also have this recorded lecture. So if some of those work out, you don't have to pick one. You could say, oh, I'm okay with these 3, or I'm okay with these 4, or all of the time slots. Is that making sense? Now, I need to verify that you are who you say you are, so if you can get out your Arizona driver's license, I'll validate that you're voter approved and we can move on. Oh, if you have your Social Security card, I'll take that too. You can just leave that on the table as you exit. And then next time we will have you with your credit card and password. What are we doing on Tuesday? I don't know. We're going to be lecturing a lot if I don't hurry up. So Tuesday in class, we will keep going. We may move beyond where we need to be for the exam. We still have some material in Chapter 12, which is poles and zeros, but you guys are experts on that already. And we have final value theorem and initial value theorem. I think those are remaining topics in Chapter 12 that we may not cover on the exam, but it's easy to slide into Tuesday's lecture. And if we move beyond that, we'll start applying these directly, these S-plane techniques or S-domain, to circuit problems directly. Yes? I'll try to post another practice exam online is the idea. Okay, so now make sure your name gets on that. And did everyone understand what I want? So don't give me lecture notes. That's what some people gave me on the calculator problem. When I asked what calculator do you use, I was seeing the result of the expression, and I didn't see a calculator. But now give me a time. If you don't give me a time, I'm assuming you're okay with any of the times. And I could even toggle that P to an A, so it could be AM. But I'll announce that, I'll try to make that announcement on the website, because if it's Monday, we'll have to have the review before I see you again officially. Yes? So stay tuned. Look on the news page of the D2L website for which one seems to win, which time slot. Let's look at another approach. Have you guys seen these before on finding the partial fraction expansion coefficients? These techniques? Let's look at a common denominator approach. So in this one, we've obtained a common denominator. Once we have that common denominator, we are going to have an expression on both sides of the equality sign in the numerator, and in those two numerators, we will equate coefficients. And once we have those powers of s, we can identify the coefficients. Now we have that many equations to work with. And we can solve the equations. For those unknown coefficients. Here is our example again. We have f of s equaling 2s plus 1 over s plus 1 squared plus, and that we said was equal to these three terms, an a1 term, an a2, and an a3. But now what we want to do is rewrite that. We want to put that over now this common denominator. If that's our common denominator, in the numerator then we have a1 multiplied by what? Now we simply multiply it by whatever we need, such that when we did the cancellation we would end up with what we started with. I just was checking to make sure that you guys were awake after that vote. Okay? Just checking. All right. Is everybody with me? Is that making sense? What's going to scale a sub 2? And a sub 3? Is everybody clear on where those come from? And now that blue set of equations need to equal 2s plus 1. Meaning, if we now multiplied all of that out, we would end up with I'm not going to hopefully bore you with all the, but do you see that this is now s squared plus 3s, no, plus 2, and this is s squared plus 2s plus 1. When you multiply those out, and we have then a2 plus a sub 3 times an s squared. We have an a1 plus a 3a2 plus a 2a sub 3 times s, and plus, running out of room, but in here we have a 2a1 plus a 2a sub 2 plus an a sub 3. And all of that, which we don't really worry too much about, is our denominator. If we now use that numerator and equate coefficients, now you can use all of the calculators that you claim to own. If we equate the coefficient that multiplies s squared, what did we have on the left? We have 2s plus 1. What's our s squared coefficient? Nothing. So we have 0, and that's equal to whatever is on the right that's scaling s squared. And that actually would allow us to check our work if we wanted to. Now we know a2 is minus a3 or a3 is minus a2. And we've determined that that's the case, haven't we, earlier? What about if we equate the s1 coefficients? On the left we had the 2, and on the right we have a1 plus 3a sub 2 plus 2a sub 3. And finally, the constant coefficient. On the right, I believe it was 2s plus 1, so we have the 1 scaling the s to the 0 term. And on the right, we had 2a1 plus 2a sub 2 plus a sub 3. And now, because we will eventually be playing with matrices when we start doing circuit analysis, but now our coefficients in the future might include s's. Here they don't, they're constant. But we can put this into a matrix formula. How big is our matrix going to be? Oh, you guys are doing it a different way. How about if I have a 3 by 3 equaling an unknown vector? Is that okay? And now on the right, I'm sorry, on the left, I have 0, 1, 1, and I have a 0. That's the first equation. The second equation gives me a 1a1, a 3a2, and a 2a sub 3, and a 2. And the final equation gives me a 2a1, a 2a2, and a 1a1, giving me a 1. And you could solve the whole thing using this method. You wouldn't have to use case 1. You could just say, you know what, I'm going to do this in maths, and I'm going to find my coefficients. Which in this case, if this is now M, and let's say this is B, I can now say that A1, A2, A3 is M inverse B, which hopefully if we have not made a mistake, we'll get the same coefficients. Questions on that? All right. Now, let's look at the last approach that I'm working with today, which is what the textbook concentrates on, and that's this derivative method for finding a sub 2. And why did we need to find a sub 2 a different way? Just as a reminder to remind ourselves. Because we had repeated poles, didn't we? Because we had repeated poles, we couldn't use case 1. Because we're using or having case 2, we have to do it a different way. Here, let's just go back to what we had started with at the beginning of today's class. Let's say we had an n sub 2 of s. We have an s plus p1 squared and an s plus p sub 3. The partial fraction expansion for this is a1 s plus p1 squared plus an a sub 2 s plus p1 plus an a sub 3 s plus p sub 3. And this approach now is a little bit, it has a few steps. And the steps are, first we multiply all of the factors, or all of the terms, multiply through by the highest power of the root factor. Does that make sense? We're multiplying in this example everything by s, the quantity s plus p sub 1 squared. That's the first step. The next step is to actually differentiate that mess. And we differentiate with respect to s. That differentiation process, once we then evaluate at the root location, is going to get rid of a lot of the terms, all of the terms except the one we're interested in. So now we evaluate at the root location, which in this example that's repeated is this root at s equal minus p1. And in this particular case, we solve for a sub 2. But if we had a higher power factor, we would differentiate again and solve or evaluate at the root location and solve for the next one, a sub 3. Then if we had another one, we would differentiate again, plug in the root, and then solve for a sub 4, etc. In our case, let's just step it through that second order example. Step A was we have s plus p1 squared times f of s is now equal to a1 plus a sub 2 s plus p1 plus a sub 3 s plus p1 squared over s plus p sub 3. That was the first step, which is just to multiply all sides or all terms by s plus p1 squared, the highest power of our factor. The next step says we want to differentiate both sides with respect to s. What happens when we differentiate a sub 1 with respect to s? That's why we're doing this, so that gets eliminated. It's a constant. We differentiate with respect to s, that's going to be gone. What happens when we differentiate the next term with respect to s? Now a sub 2 falls out. What happens when we differentiate the next term with respect to s? A mess. But let me just do it, and then maybe you will believe that you really don't have to worry about it in the future. But now what do we have? Well, differentiating ratios, I always forget my formula, so I just go back and use the product rule, and I have my denominator with a negative power. Meaning, if I differentiated that first one, I would say, okay, that's now 2a sub 3 s plus p1 times the second factor, which was s plus p3 to the minus 1, or s plus p3. And then I differentiate the denominator, which is now minus 1 times s plus p3's derivative. And we keep the numerator term, s plus p1 squared, and this one would be s plus p sub 3 squared. That doesn't look so bad once we do the third step, which is step C in red, is when we evaluate this at minus p1. If we evaluate this, everybody see what's going to happen with those blue terms? If we plug in s equal minus p1 in both of those blue terms, they are going to vanish, and we don't have to worry about them, because we have minus p1 plus p1. That's the whole point of doing that. And all we are left with then is a sub 2 isolated on the right, and then maybe this a little bit more interesting expression on the left. We differentiate s plus p1 squared times f of s with respect to s, and then evaluate that at s equal to minus p1. So that says then that in this fourth step, we have a sub 2 is equal to the derivative with respect to s of s plus p1 squared f of s, and we will evaluate that at s equal minus p1, but that's not quite as ugly maybe as it appears, because that s plus p1 squared eliminates that term in the denominator of the f of s. In terms of how we had parameterized that before, that leaves us our numerator and just the one term downstairs, one factor, s plus p3, that we have to differentiate with respect to s. Now, the book gives you a general form. If you had something that was, let's say, a fourth order root, then you would have to do this 3 different times. So in general, let's just look at the expression and make sure that we're okay with it. Here's what we would have. We would have f of s equaling, let's say, n of s over s plus p sub 0 to the little n. Notation-wise, we have a1 over that factor to the n. We have a sub 2 over that factor to the n minus 1. And we just keep going until we end up with just that factor. So that's the expression that we're dealing with. And in terms of the way that we've defined those a's, we can now say that each of those a's, let's say a sub j, is now going to be defined as 1 over j minus 1 factorial, the j minus first derivative with respect to s of this term s plus p sub 0 to the n f of s. And we would then evaluate that each time at s equal minus p sub 0, where we let j run over all of these different values from 1 all the way up to n. Meaning, let's just look at some of the limiting cases. What if we had j equal 1? That's A1, and that's actually case 1, isn't it? So we shouldn't have to differentiate for that case. But we have 0 factorial. Good. So this is 1. We're okay there. What does this do? We now have the 0th derivative, right? And we're just multiplying s plus p 0 to the n times f of s and evaluating it minus p naught. So that's okay. Now if we plug in a or j equal 2, we will get a sub 2, and that will be our first derivative piece. We now have 1 over 1 factorial. 1 factorial again is 1. And we differentiate that expression once with respect to s and let s equal minus p sub 0. If little n was 5, then we would have to keep doing this 1, 2, 3, all the way up to 5. So we would have 4 derivatives to process. The first one doesn't happen. J equal 1. Are we okay with that? Or is it clear? Maybe you're not okay with it, but questions? Let's look at an example. So let's say that we have the following. Let's say v of s. For some reason now I've changed from f to v, just to make sure you're still awake. We have s squared plus 3s over s plus 1, s plus 2 cubed. What's the partial fraction expansion structure look like? Or where, okay, so let's just sort of do an aside. Where are my zeros for this transform? My zeros. So you have to factor the numerator. And that's s, and then s plus 3. Yes? So where are my zeros? At the origin and at minus 3. Where are my poles? That's what people were wanting to answer. I have one pole at minus 1, and I have 3 poles at minus 2. Which of those poles dominate my response? The minus 1. And how long would you have to wait for your transient to decay if this were actually a transfer function? 5 seconds. Is that making sense? Now, what's the structure of the partial fraction expansion? And let's start with the s plus 2 piece. Are we okay with that? And which of these can we find pretty quickly? A1 and A4. We can use case 1. If we do A4, we multiply both sides through by s plus 1, and we let s equal to minus 1. We have s squared plus 3s over s plus 2 cubed. One minus 3 all over 1. Is that true? A sub 4 is minus 2. A sub 1 is going to be s squared plus 3s all over s plus 1 evaluated at minus 2. And what's that one? So we have 4 minus 6, or minus 2, divided by minus 1, and we have 2. So now let's find a sub 2. This is now, using our formula, we say this is now j equal 2. We now have 2 minus 1 factorial. And what do we have up in this? We have s squared plus 3s over s plus 1. That's what happens when we hit f of s with s plus 2 quantity cubed. We're just left with that piece. And then once we do that, we will evaluate it at s equal minus 2. And we have then 1 over 1, and we simply have one derivative of that expression. So we could do that many different ways, but let's just say that we have 2s plus 3 over s plus 1. That's the first times the derivative of the second, where my second is the denominator term, plus the first, which is my numerator, times the denominator's derivative. That's where the minus sign comes from. And I now have s squared plus 3s over s plus 1 squared. And it may be to our advantage to actually simplify this, because we're going to need to differentiate it again, right, with respect to s. So I'm not going to, I'll let you do this tonight. I know that you want to do that. And some of your calculators will do this. Maybe not in the way that we're doing it. But we now have that expression inside the square brackets that we can differentiate one more time. But if we evaluate this at s equal minus 2, we end up with 3 for a sub 2. And let me just now put a sub 3 in there, the expression, since we have about 30 more minutes to go, judging from the way people are shuffling in their chairs. We now have 1 over 3 minus 1 factorial and now we're taking the second derivative of what we had before, but we've already determined what the first derivative of that was, so let's not do that again. And we have a 1/2, and then we differentiate once this piece that we had before, s squared plus 2s plus 3 over s plus 1 squared. So we just need to differentiate that piece with respect to s. Does everybody see what I'm trying to get you to understand or appreciate? And I will probably only repeat a poll maybe 9 times on the exam. And maybe we'll have 3 other roots, so you'll have a 12 by 12 matrix if you do it by the common denominator method. We will pick up at that point, and I'll try to tabulate your vote. Hopefully we won't have a hanging chad, and we'll see when we have our review.